Good day, everyone. I hope you are all well, safe, and healthy. Welcome to our Lecture 7 on methods of integration, specifically on outlines, integration by parts, and rational fractions. This is the end topic of Chapter 2 in Calculus 2, based on the shared syllabus. Now, our lecture for today is guided with this technical knowledge. First is to evaluate given integrals using integration by parts method. Secondly, to integrate rational and irrational fractions whose denominator first contains factors that are linear and then repeated, and second, denominator contains irreducible quadratic factors that are non-repeated. Let's start with integration by parts. So what is this method known as integration by parts? And what do you think is the reason why it's called integration by parts? Now, suppose u and v are differentiable functions of x, where we call the derivative of product of functions u and v. That is, from what we learned in our calculus 1, we know that the derivative of the product of the functions u and v with respect to x is equal to the sum of two products. First product is the product of the function u of x and the derivative of v with respect to x. And the second product is the product of the function v of x and the derivative of the function u with respect to x. Supposedly, we are to evaluate a certain integral whose integrand is the product of two functions. Now, out from this derivative of product of u and v, we can derive a formula or an equation to evaluate that certain type of integral. So using derivative of product of u and v, we can solve for the product of the function u of x and the derivative of v with respect to x as simply the difference between the derivative of the product of u and v with respect to x and the product of the function v of x and derivative of the function u of x. Now, integrating both sides of the equation, we get for the expressions on the left side of the equation, we integrate that. So we have integral of the product of u of x and the derivative of v with respect to x is simply equal to, we integrate each expression or each term in the right hand side of the equation. And so we have the integral of the derivative of the product of functions u and v with respect to x minus the integral of the product of the function v of x and derivative of u with respect to x. Simplifying this operation, we get the general formula for integration by parts method. We have the integral of the product of u of x and the derivative of v with respect to x is equal to simply the product of functions u and v with respect to x minus the integral of the product of the function v of x times the derivative of u with respect to x. So this is our general formula for integration by parts method. Take note, this method of integration is helpful when the integrand is a product of two kinds of function, as I have said a while ago. If we are to evaluate an integral whose integrand is a product of two functions, then we can use integration by parts method. However, that depends. The ability to uh, decide whether integration by parts method will work depends on you. It depends on me on how I able to see the pattern in the integrand. Okay, we are dealing with the integrand. We examine the integrand, and if this integrand is a product of two kinds of function, then we can use this method of integration known as integration by parts. So say, for example, we are to evaluate the integral of x times e raised to the power of x dx. We let the first factor be our function u of x. And we let the second factor in the integrand be our derivative of the function v with respect to x. Note, u or functions u and v should be chosen in such a way as to make the integral of dv easy to evaluate. So our concern now is what factor will be identified or will be labeled as function u of x, and what factor of the integrand will be labeled as the derivative of the function v with respect to x. In this example, can we have e raised to the power of x as our function u of x? Or can we say that x dx is our derivative of the function of v with respect to x? Remember, in choosing or in labeling the factor that will be represented as the function u of x and the derivative of the function v of x, we have to remember that the integral of dv is easy to evaluate. Now let's see if having these representations of the function u of x and derivative of v with respect to x will make the process of integration easy. Let's see. Now we let the first factor in the integrand as our function u of x. And we let the second factor, which is e raised to the power of x dx, as our derivative of v with respect to x. We call the general formula of integration by parts. we already have the value for the function u of x, and that is x. We also have, we will be looking for the value of the derivative of the function u with respect to x. But how? How can we determine the value for the derivative of the function u with respect to x? That is, we will differentiate function u with respect to x. Now, the derivative of the function u with respect to x is simply the first derivative of x. And the first derivative of x is 1. And so we have equals dx because we are integrating with respect to x. And so we have the value for the derivative of u with respect to x, and that is dx. Also, we will be evaluating the value for v of x, for the function v of x. But how can we determine the value of this function v of x? We all know that from the given integrand that we have, we label e raised to the power of x dx as our derivative of v with respect to x. Now, having this derivative of function v with respect to x, which is equal to e raised to the power of x dx, we can determine the value of the function v of x. How? By simply integrating this derivative. Again, to find the value of the function v of x, we integrate the derivative of the function v with respect to x. Therefore, we will integrate e raised to the power of x dx. And v of x, or the function v of x, is equal to e raised to the power of x. Now, we will substitute these values of the function u of x, of the function v of x, and the derivative of the function u with respect to x to our general formula. And so we have x times e raised to the power of x, which is the value of the function v of x, minus the integral of the value of v of x, and that is e raised to the power of x, and the value of the derivative of the function u with respect to x, which is dx. Simplifying, we get x times e raised to the power of x minus the integral of e raised to the power of x dx is simply e raised to the power of x plus c. Since our first term and second term contains common term, we factor out that common term, which is e raised to the power of x times x minus 1 plus c. And so the integral of x times e raised to the power of x dx is equal to the product of e raised to the power of x and the quantity x minus 1 plus c. Now let's have example number 2. We will evaluate the integral of x squared sine x dx. First thing to do is to examine the integrand. Do the integrand represents product of two functions? And which of these two factors will be labeled as function u of x? And which will be labeled as the derivative of v with respect to x? Now in this case, we label the first factor x squared as our function u of x. And we label the second factor sine x dx as the derivative of the function v with respect to x. We call the general form of integration by parts method. So we already have value for the function u of x. Now given that value of the function u of x, we can find the derivative of the function u with respect to x. That is the first derivative of x squared. That is 2x dx. We will also evaluate the value of the function v of x. How are we going to do that? We all know that the derivative of the function v with respect to x is sine x dx. Now having that derivative of the function v, we can find or determine the value of v by integrating that derivative of the function v. So we integrate the derivative of the function v with respect to x. That is equal to the integral of sine x dx. Therefore, the function v of x is equal to negative cosine x, because the integral of sine x dx is negative cosine x. Then we will substitute these values of the function u of x, the function v of x, and the derivative of the function u with respect to x to our general form. So we have the integral of x squared sine x dx is equal to the product of the functions u and v. And so we multiply the value of the function u of x, that is x squared, and the value of the function v, which is negative cosine x. Multiplying these two, we get negative x squared cosine x minus the integral of the product of the value of the function v of x. The value of the function v of x is negative cosine x times the derivative of the function u with respect to x, which is 2x dx. Simplifying this, we get negative x squared cosine x plus 2, applying integral of the product, plus 2 times the integral of x cosine x dx. However, our second term still needs to be evaluated further. And by examining the integrand of the second term, we see that it's a product of two functions. The product of x and cosine x dx. Therefore, we will use again the general form of integration by parts method. So we let the function u of x be equal to x. And we let the derivative of v with respect to x be equal to cosine x dx. Then we differentiate the function u with respect to x, and that is dx. And we integrate the derivative of the function v with respect to x. We get integral of cosine x dx, which is equal to sine x. And so the value of the function v of x is equal to sine x. Making use of the general form of the integration by parts method, we have negative x squared cosine x plus 2, the constant of the factor of the second term, times the quantity. Now, take note, the expressions inside the quantity were derived using the general form of the integration by parts method. Therefore, we are using the integration by parts method twice in this example. Okay, so let's proceed. Simplifying the operation, we have negative x squared times cosine x plus we distribute 2 to the terms inside the expression. We get 2 times x sine x is 2x sine x minus 2 times the integral of sine x dx. The integral of sine x dx is negative cosine x. And so we have negative 2 times negative cosine x plus c. Simplifying further, we get the final answer. And so the integral of x squared sine x dx is equal to negative x squared cosine x plus 2x sine x plus 2x cosine x plus c. Again, let's recall the things that we did a while ago. First, given this integral, we examine first the integrand, then we label our functions u of x and the derivative of the function v with respect to x. Then find the necessary values for the remaining terms or quantities in the general form of the integration by parts method. Then, having obtained the required values for the terms and quantities of the general form of the integration by parts method, we substitute them, and then we perform the required operations. Then we found out that the second term of the general form contains product of two functions. I'm referring to the expressions in the integrand, this x times cosine x dx. We are integrating product of two functions, x and cosine x dx. And so the concept or the process of integration by parts come into play again. And then we made use of that method integration by parts. And then we perform the required operations. We simplify the answer and we simplify the solution, and then we arrive to the final answer. That's it. Now let's proceed to the second outline of this lecture on integration of rational fractions. We have here examples of rational fractions. And one of these four is an irrational fraction. That means three of these four are examples of rational fractions. But what is rational fraction, by the way? A rational fraction is a quotient of two polynomials having real coefficients and no common factor other than 1. Now, rational fraction can be represented through this form, the quotient of two polynomials, n of x and d of x. If the degree of the numerator, or if the degree of the polynomial n of x is less than the degree of the denominator for the polynomial d of x, then this fraction is a proper rational fraction. The first three examples are examples of proper rational fraction. What makes them a proper rational fraction? Let's have the first example. Our numerator has a leading term x squared, and so the degree of the numerator is 2, or it's quadratic, second degree. And the degree of the numerator, by mere examination, we are multiplying 3 x's. So we get x raised to the power of 3, or x cubed. And so the degree of the denominator is third degree, or cubic polynomial. Now, since the degree of the numerator is less than the degree of the denominator, then this is an example of a proper rational fraction. The same thing goes with the second example and with the third example. But how about the last example? Is this a proper rational fraction? You got it right. It's not a proper rational fraction because the degree of the numerator is not less than the degree of the denominator. So what do we call this example? If it's not a proper rational fraction, then it's the complement, it's an improper rational fraction. Now, what's the purpose of defining proper rational fraction and improper rational fraction? If the given integral contains a proper rational fraction, how do we evaluate that integral? Say, for example, we have the integral x squared plus 9x plus 2 all over the product of the three factors x minus 1, x plus 1, x plus 2 dx. How do we evaluate this integral? Now, in evaluating the integral of a proper rational fraction, it is important to represent the given fraction to some of simpler fractions called partial fractions. And transforming our integrand into partial fractions, we get the integral of the quantity 2 over x minus 1 plus 3 over x plus 1 minus 4 over x plus 2 dx. Wait, How did we get that? Thus, to integrate a proper rational fraction, we simply integrate its equivalent partial fractions. Later, I'll discuss on how to transform that given proper rational fraction into partial fractions. As of the moment, you have to remember that to integrate a proper rational fraction, first you need to get its equivalent partial fractions. Once you get the equivalent partial fractions, that's the that's that signifies that we need to start integrating the integrand or the given integrand. But what if the integrand is an improper rational fraction? How do we integrate the integral? Say, for example, we have the integral of x cubed plus 5x squared plus 9x plus 7 all over x squared plus 5x plus 4 dx. This is an example of an improper rational fraction because the degree of the numerator is not less than the degree of the denominator. In evaluating the integral of an improper rational fraction, it should first be reduced by division into a polynomial and a proper rational fraction. Therefore, what it says here is, if the integrand is an improper rational fraction, we will apply first polynomial division. And if you can still recall polynomial division, that is the same with long division. However, it involves algebraic terms, algebraic expressions. Now, in this case, to apply polynomial division, we simply divide the numerator by the denominator. So we divide x cubed plus 5x squared plus 9x plus 7 by x squared plus 5x plus 4. Now, after applying polynomial division, it will give us this form. So the given integrand will now be reduced to sum of a polynomial q of x and the proper rational fraction r of x over d of x. The first term is a polynomial and the second term is a proper rational fraction. Now, if it's a proper rational fraction, then there is still a need to transform this proper rational fraction into partial fractions. That's it. So where q of x is a polynomial and r of x over d of x is a proper rational fraction, it is r of x over d of x, or the proper rational fraction, that should be resolved or broken up into partial fractions. But remember, we are not integrating the partial fractions only, but we will be integrating the polynomial q of x. A factor of the type ax plus b is called a linear factor. And if this linear factor is being raised to, say, n, where n is greater than or equal to 2, or if this form of factors occur in d of x or in the denominator, then ax plus b is a repeated linear factor of the denominator. Now, a factor of the type ax squared plus bx plus c is called a quadratic factor. It's quadratic because it's in the polynomial is in second degree, or the factor is in second degree. And it is said to be irreducible if it cannot be factored further into real linear factors. If ax squared plus bx plus c is irreducible, and this quadratic factor is being raised to n, or if this quadratic factor being raised to n occurs in the denominator d of x, then ax squared plus bx plus c is a repeated and irreducible quadratic factor. So what we need to remember here is, when can we say that it's a linear factor? Or when can we say that the factor is a linear factor? If the factor is a linear factor, when can we say that it's repeated or not repeated? Or some other references would say non-repeated linear factor. Or if the factor is a quadratic factor, is that quadratic factor irreducible or not? If it is irreducible, or say the quadratic factor cannot be factored further, I'm sorry. Okay. So if the factor is a quadratic factor, is that quadratic factor a repeated quadratic factor or a non-repeated quadratic factor? Let's have case number 1. When the factors of d of x are all linear and none is repeated, continuation of this case is when the factors of d of x are all linear and some are repeated. However, that case is not included in this lecture because because in this lecture we will focus only on non-repeated factors. Maybe we can have the other cases on our next lectures. Cross finger to that. Now, to each non-repeated linear factor ax plus b, there corresponds a partial fraction of the form a over ax plus b, where a is a constant to be determined. Example, we are to evaluate the integral of x squared plus 9x plus 2 all over the product of the three linear factors x minus 1, x plus 1, x plus 2 dx. Examine the denominator. All factors are linear factors, and each linear factor is non-repeated because they are unique. X minus 1 is different from x plus 1, and it's different from x plus 2. And so, every non-repeated linear factor corresponds a partial fraction of the form a over ax plus b. For in this case, we have 3 partial fractions. And so, we get x squared plus 9x plus 2 all over the product of x minus 1, x plus 1, x plus 2 is equal to a over x minus 1 plus b over x plus 1 plus c over x plus 2, where this A, B, and C are that need constants that need to be determined. And the denominator of each constant are the non-repeated linear factors of the integrand. Now our next task is to determine or to find the values of these constants A, B, and C. But how? How are we going to determine the values of these A, B, and C constants? We will apply the procedure known as partial decomposition method. How? Okay, so we will equate the given integrand. Make sure that our given integrand is a proper rational fraction so we can directly proceed to expressing it into partial fractions. Okay, then we will multiply both sides of the equation by the factors x minus 1, x plus 1, x plus 2. Now we will evaluate first the expression on the left-hand side of the equation. What will happen if we will multiply the non-repeated linear factors to our integrand? Take note that the multiplying factor is the same with the denominators of the given integrand, and so it will be eliminated. So what remains is x squared plus 9x plus 2. Now, how about with the right-hand side of the equation? So first thing is, we will apply distributive property here. So we will multiply the three factors to the first term in the right-hand side of the equation. And x minus 1 will be eliminated. So what remains is a times x plus 1 times x plus 2. How about if we multiply the factors to the second term? What factor will be eliminated? Oh, it's x plus 1. And what remains is a product of b, x minus 1, and x plus 2. And the same process applies to the third term of the right-hand side of the equation. X plus 2 will be eliminated, and so we have the product of c and x minus 1 and the x plus 1. And so we get x squared plus 9x plus 2 equals the product of a, quantity x plus 1, the quantity x plus 2, plus the product of b, quantity x minus 1, quantity x plus 2, plus the product of c, quantity x minus 1, and x plus 1. Simplifying, we simplify the expressions on the right-hand side of the equations, and we get this. We apply here the famous FOIL method. First term, outer terms, inner terms, and the last term. And so we get a times x squared plus 3x plus 2 plus b times x squared plus x minus 2 plus c times x squared minus 1. Simplifying further the expressions on the right-hand side of the equation, we get ax squared plus 3 ax plus 2a plus bx squared plus bx minus 2b plus cx squared minus 1c or minus c. Then we will group these terms according to their degrees. So ax squared will be grouped or associated with bx squared and cx squared. 3ax will be associated with 3a and bx. And 2a will be associated with minus 2b and minus c. And then factor out common term. So we have the quantity a plus b plus c times x squared plus the quantity 3a plus b times x plus the quantity 2a minus 2b minus c. Moving forward, so this is the last step in the previous slide. We have x squared plus 9x plus 2 is equal to the quantity a plus b plus c times x squared plus 3a plus the quantity 3a plus b times x plus the quantity 2a minus 2b minus c. Since this is an equation, therefore, we will equate we all know that a plus b, a, b, and c are constants. Therefore, referring on the expressions on the right-hand side of the equation, this a plus b plus c is a numerical coefficient of x squared. And we will equate this a plus b plus c to the numerical coefficient of x squared in the left-hand side of the equation. So we have x squared implies a plus b plus c equals 1. We are simply equating the corresponding numerical coefficients of the corresponding degrees of x. And moving forward, 3a plus b is the numerical coefficient of the variable x. And we will equate this numerical coefficient 3a plus b to the numerical coefficient of x in the left-hand side of the equation, which is 9. And lastly, we will equate 2a minus 2b minus c to the constant in the left-hand side of the equation, and that is 2. Remember, our goal here is to evaluate the integrand. But how can we evaluate the integrand if we do not know the values of a, b, and c in the partial fractions? And so we need first to find the values of a, b, and c. So given these three equations, we can determine the values of the constants a, b, and c. How? We can use elimination method here. We will eliminate one or two variables so we can solve the remaining or the other variables. Or we can use substitution method, expressing certain variable in terms of the other variables and then substitute this new or this derived value to the other equation and then solving for A or B or C. But here I'll present to you the elimination method. So we will be eliminating variables in order to solve for the other variables. So I'll start with the first equation and the second equation. In this case, I'll try to eliminate constant b. Okay, but to eliminate constant b, I need to multiply the first equation by -1. So constant b will be eliminated. How is it possible? So when we multiply -1 to each term of the equations, we get -a minus b minus c equals -1. Then copy the second equation, 3a plus b equals 9. So the constant b will be eliminated. And then we add the remaining terms of the equations. So -a plus 3a is positive 2a. b is eliminated. Minus c is, minus c equals -1 plus 9 is positive 8. The next, I'll deal with the second equation and the third equation. 3a plus b equals 9 and 2a minus 2b minus c equals 2. Since in the first round of elimination, I eliminated b, the same thing I will do with the second and third equations. So I will try to eliminate b. The purpose of that is for me to deal with, if b is eliminated, then I will deal with constant a and constant c. And then same process will apply. I'll eliminate one constant again until I get the value of one constant, and then resubstitute that value to the given equations so I can get the values of the other constants. But let's have first these second and third equations. I will eliminate b. How? So I will multiply positive 2 to the second equation. So I have here 2 times 3a plus 2 times b equals 2 times 9. So I get 6a plus 2b equals 18. Then I'll add this second equation to the third equation. We all know that b will be eliminated because they are opposite. So 6a plus 2a equals 8a. Positive 2b and negative 2b will be eliminated. Copy minus c equals 18 plus 2 is 20. So I have here 2a minus c equals 8 and 8a minus c equals 20. 2a minus c equals 8. We get this by eliminating constant b in the first and second equations. And I get 8a minus c equals 20 by eliminating constant b in the second and third equations. Now I'll deal with these two. I'll try to eliminate, I'll try to eliminate c. But how? How am I going to eliminate c here? So I will multiply -1 to the first equation. So it's -1 times 2a is -2a. -1 times -c is positive c. -1 times 8 is -8. And then I will add these two equations. C will be eliminated because they're opposites. So -2a plus 8a is positive 6a. And -8 plus 20 is positive 12. Simplifying further, I get the value for the constant a, which is 2. Now I can solve for the value of b and c. Substituting a to, say, where will we substitute a? The value of a. Okay, I'll use the second equation because it contains only two variables. I mean, two constants, a, b, and a is given. So 3 times a, the value base 2 is 6. So b is equal to 9 minus 6, or b is equal to 3. Now having these values of a constants a and b, I get the value of c, which is negative 4. Wait, we are not yet done. All we have here are the values of the constants a, b, c, which are highly needed for our partial fractions. Okay, let's proceed. We have that. Then we substitute the value of a, b, and c. So we have 2 over x minus 1, 3 plus 3 over x plus 1 plus negative 4 over x plus 2. This is the expressions that we will integrate now. Okay, so integrating x squared plus 9x plus 2 all over x minus 1 times x plus 1 x plus 2 dx is the same as evaluating these partial fractions with respect to x. Okay, so now we will evaluate, or we will integrate the partial fractions, these three partial fractions with respect to x. But before that, remember that these partial fractions are equal to the original integrand. We just decomposed this integrand into partial fractions. Okay, and then we will apply integral of sum or linearity rule. So we have integral of 2 over x minus 1 dx plus integral of 3 over x plus 1 dx minus integral of 4 over x plus 2 dx. Then we will apply integral of product. So we have 2 times integral of 1 over x minus 1 dx plus 3 times integral of 1 over x plus 1 dx minus 4 times integral of 1 over x plus 2 dx. So I guess we'll arrive to the final answer by examining the integrand. One standard formula under integration of, what's that? Integration of logarithmic functions. That is under theorem 13 of our lecture. It says in theorem 13, the integral of dx over x, or the integral of du over u, where u is a function of x, is equal to the natural logarithm of u, the natural logarithm of the absolute value of u plus c. And so we get the final answer. So the answer is 2 times the natural logarithm of the absolute value of x minus 1 plus 3 times the natural logarithm of the absolute value of x plus 1 minus 4 times the natural logarithm of the absolute value of x plus 2 plus c.